Nkomati Mine is located in Mpumalanga Province, South Africa, about 300 kilometers east of Johannesburg and 500 kilometers from Richards Bay Port. This location offers easy access to major industrial hubs and export markets. The mine lies in the globally significant Bushveld Igneous Complex, the world's largest layered mafic intrusion, hosting extensive nickel, platinum, chromium, and vanadium deposits. The surrounding area is characterized by rolling hills, a subtropical climate, and access to essential water resources from the Komati River basin, all of which support efficient mining operations. The mine's resource base consists of copper-nickel sulfide ores, which are critical for industries like stainless steel and electric vehicle batteries. In 2019, Nkomati processed 3.5 million tons of ore with an average nickel grade of 0.26%. Table shows the product concentration in ore for 3 years. Infrastructure supporting operations. The mine's infrastructure is designed to maximize efficiency. It uses open pit and underground mining methods, supported by trackless mining equipment, conveyor belts for transporting crushed ore to concentrator plants, reducing reliance on haulage trucks, on-site concentrator plants equipped for flotation, milling, and secondary crushing, ensuring high recovery of nickel and byproducts like copper and cobalt. Include reliable power from South Africa's national grid and water recycling systems to reduce environmental impact. Additionally, an internal road network and Richards Bay Port streamline transportation and exports. Suitability for factory end product. Nkomati's nickel sulfide deposits are high grade, making processing economically viable. With rising global demand for nickel in stainless steel and lithium-ion batteries, establishing a factory to produce refined nickel or nickel sulfate is a strategic opportunity. Existing infrastructure such as concentrator plants and transport systems supports factory development. Proximity to Richards Bay Port ensures cost-effective export logistics, while access to global markets makes Nkomati ideal for scaling operations. Sustainability and market prong. Environmental sustainability and market adaptability are crucial for long-term success. Integrating renewable energy sources like solar or wind can address South Africa's power challenges. Advanced waste management systems will minimize environmental impact. With global nickel demand expected to rise, investing in high-purity nickel production at Nkomati offers significant growth opportunities. South Africa's strategic location provides easy access to Asian and European markets.
Class 1 nickel refers to high purity of nickel content that are greater than 99.8%. So in this manufacturing process, due to the reason that the type of nickel required for lithium-ion batteries is nickel sulfate, we will be focusing more on producing Class 1 nickel. Nickel plays a critical role in the production of lithium-ion batteries, particularly in the cathode materials, which influence the battery's energy density and lifespan. The process begins with mining nickel from its natural ores, primarily laterites and sulfides. Laterite ores are commonly found near the surface and are extracted using open pit mining. This involves clearing vegetation, blasting the ore, and transporting it to processing facilities. Sulfide ores, in contrast, are mined through underground methods such as drilling and blasting. After extraction, the ore undergoes processing to isolate and purify nickel. For laterite ores, the process is energy intensive and involves techniques like high-pressure acid leaching, HPAL, or pyrometallurgy. In HPAL, the ore is subjected to high-temperature acid solutions which dissolve the nickel, forming a solution that can later be precipitated as a mixed hydrogen precipitate MHP or mixed sulfide precipitate MSP. Pyrometallurgy, on the other hand, uses heat to separate nickel from impurities, often producing ferronickel or made as intermediate products. For sulfide ores, the process is generally simpler. The ore is crushed and ground into smaller particles before being concentrated through flotation. This step separates nickel-bearing minerals from the waste material. The resulting concentrate is then smelted at high temperatures to produce a nickel matte, which undergoes further refining to chemical or electrolytic methods to achieve battery-grade nickel. State, it is utilized in manufacturing cathode materials for lithium-ion batteries, starting with the production of nickel sulfate. Refined nickel is dissolved in sulfuric acid under controlled conditions, typically at ambient to slightly elevated temperatures and at atmospheric pressure, to produce a highly pure nickel sulfate solution. Advanced filtration systems, such as filter presses, are used to remove impurities during this stage. The solution is subsequently crystallized in industrial crystallizers such as forced circulation evaporators to obtain solid nickel sulfate crystal. The nickel sulfate is then used in synthesizing cathode materials such as nickel cobalt manganese NCM or nickel cobalt aluminum NCA. This step involves combining nickel sulfate with cobalt sulfate and manganese sulfate, or also can be used aluminum sulfate in precise stoichiometric ratios. These solutions are mixed in reactors equipped with high shear mixtures to ensure homogeneity. A lithium source, typically lithium hydroxide, is then added to the mix. The reaction occurs at temperatures around 60 to 90 degrees Celsius under constant stirring, forming a co-precipitate intermediate precursor. The co-precipitation process is carried out in continuous tank reactors or CSTRs with strict control of pH around 10 to 11. The calcined cathode material is often coated with a thin protective layer to improve its stability and prevent unwanted side reactions during battery operation. Materials such as alumina or lithium phosphate are commonly used in this coating, which is applied using atomic layer deposition (ALD) or chemical vapor deposition (CVD) techniques. The finished cathode materials is then processed into electrodes. A slurry is prepared by mixing the cathode powder with a conductive binder such as polyvinylidene fluoride (PVDF) and a solvent like N-methyl tupyrrolidone. This slurry is coated onto thin aluminum foils using precision slot die cutters and then dried in industrial drying ovens at temperatures of 120 to 150 degrees Celsius to remove the solvent, leaving behind a uniform coated film. In parallel, the anode, typically made from graphite, undergoes a similar process. The two electrodes are pressed with separator usually made from polyethylene or polypropylene and an electrolyte solution containing lithium salts dissolved in organic solvents such as ethylene carbonate and dimethyl carbonate. The assembly of these components into battery cell is carried out using automated stacking or winding machine in clean room environment to prevent contamination.
Since extraction of nickel processes commonly involve the removal of large volumes of overburden, this can cause to habitat destruction and increase sedimentation in nearby water bodies, which affects the aquatic life. Laterite nickel mines can produce significantly higher carbon emissions compared to sulfide mines. This highlights the need for improved mining practices that minimize carbon footprints and enhance energy efficiency. Leaching of nickel and other heavy metals into nearby water sources can lead to toxic conditions for aquatic ecosystem and poses health risks to local communities. To overcome this environmental concern, introduction of advanced technologies such as adoption of renewable energy sources in mining operations such as solar, wind or hydroelectric power can help to reduce reliance on fossil fuels. Optimizing mining processes also through automation and digital technologies can lead to substantial reduction in energy consumption and emissions. Management of methane emissions, particularly from sulfide ores, by implementing methane recovery system can capture this gas for use as energy source, thus preventing its release into the atmosphere. Adopting a life cycle sustainability assessment LCSA framework can help mining companies evaluate the environmental impacts of their operation comprehensively. This approach allows to nickel-based compounds have been identified as possible candidates for nickel-lithium batteries due to their excellent electrochemical characteristic and high energy density. In addition to electrochemical capabilities, nickel-based materials' environmental compatibility and cost-effectiveness are important variables determining their use in commercial battery systems. MPRDA was introduced by the government of South Africa to ensure that mineral sources were used in a proper way that benefits all parties. This act mainly emphasized responsibility for the mining companies to practice mining methods that environmentally friendly and sustainability, also community welfare. MPRDA also requires the mining companies to develop social and labor plans (SLPs), which highlighting that how they as the party that responsible for the mining resource contributes to the socio-economic development of the communities at the locality that they were mined. In addition, broad-based socio-economic empowerment charter was introduced by the government to address the inequalities due to the apartheid era policies. These charters establishes the specific targets for the inclusion of historically disadvantaged individuals in the mining sector, including provision for ownership, management, and procurement.